Oxford, and he's a well-known Bayesian and author of a textbook on data analysis and a few other textbooks. And he's very kindly consented to come here and tell the talk.
Thank you very much. Thank you for inviting me here. Let's go and share. Right, so for the benefit of the previous speaker, I'm one of these awkward physicists. Although he said Ed, James and Jeffries weren't too bad, so that's the school I come from, so perhaps I'm just about passable. But I did actual sciences as an undergraduate, so I'm principally a physicist. I'm to some extent a chemist and to an even lesser extent a cell biologist as well. So, right. So this is like the organisers here. I never learnt about this as an undergraduate. I learnt about this when I was a research student. And all of a sudden, because being a scientist, I had to analyse data, or at least I thought I did. And I never really understood it as an undergraduate. Wasn't taught it properly, and it didn't make much sense. And then somebody said, there's another way of looking at data analysis. And that's what I'm going to present to you today, because it made more sense to me. And over the years, I've explained it to my experimental colleagues. And their views usually, they've heard of the word Bayesian, they don't really know what it is, they're a bit scared. And they say, oh, we just do ordinary analysis. And so this is an introductory talk, mainly aimed at trying to persuade them that it isn't that difficult. And they might not have known it, but they were already doing quite a lot of Bayesian analysis already. So I'm only going to have time to go through this very briefly. If you want to look at it more carefully, this is the introductory book I wrote many years ago in '96, and John Skilling kindly added a couple of chapters, and when I revised it, he put in an appendix on his sort of modern take on the Cox axioms and the Cox development as well. But the examples I'm going to use in this talk come from reflectivity analysis, and details of that you can find here. Okay, so the background, the ideas go back about 300 years, and I listed 3 people, or it looks like 3 people, but actually there are more than 3 because there are at least 2 famous Bernoulli brothers. But during their time, the Bernoullis were a large family of famous mathematicians, uncles and fathers and grandfathers. But 2 are still popular, and both made contributions to probability. Then we have the Reverend Bayes, and the person who really started doing Bayesian analysis was Laplace, who applied it to all sorts of problems. And there are other people I left off. You could put in Gauss and Pascal and others too. And I'm really talking about people who developed probability theory as a tool for reasoning in situations where you couldn't argue with certainty. So this is when you got bored with tossing coins and playing cards, but you wanted to use it to actually do some science to learn about the world. And that's what Laplace really started doing. And one of the problems Laplace did was he estimated the mass of Saturn. A friend who's an astronomer was observing the orbital periods of one of the moons of Saturn. He knew about Newtonian gravity, had some estimate of big G, and using all that information he tried to estimate the mass of Saturn. I don't think he actually drew a picture like this, but in modern parlance he drew a picture, he plotted the mass of Saturn here, the probability of mass given the data and his knowledge about big G and everything else, and got some sort of bump. And the interpretation would be that the fraction of the area between M1 and M2 represents how much Laplace thinks the mass lies in that range. And so if the probability bump is like that, you might say where the maximum is represents your best estimate in some sense, and the spread of this curve gives you your uncertainty. The broader the peak, the more uncertain you are. The sharper the peak, the less uncertain you are. And he stated how confident he was in his estimate in the following way. He said it would be like a bet of 11,000 against 1, but the error of the result is not 1/100th of its value. So basically he's saying he knows the answer pretty well to within 1%. He didn't make such a bet. He was just saying this is one way of thinking about the how confident he was in the result. But soon after Laplace died, people, of course, started to reject this view of probability. This view really relied on probability being a degree of belief, state of knowledge, coding of uncertainty, however you like to think about it. And, you know, people like Venn and so on decided that this, what's this notion of degree of belief? They thought it was too vague a notion to be the basis of rigorous mathematical theory, so they redefined what probability meant as a long-term relative frequency, because that's something you could measure. Well, not in principle, because you can't do an experiment infinite number of times, but at least in principle you might. Well, this all sounds very nice, except you can't do anything very useful with it. For example, you can't do this problem. The strict frequency interpretation says this graph makes no sense. Saturn has a certain mass. If its mass, whatever its mass is, it doesn't fluctuate. If it doesn't fluctuate, it doesn't have a frequency distribution. So what do you mean by the positive mass? You know, in a strict frequency interpretation, that doesn't make sense. If they had to interpret it, they might think about an ensemble universes in which everything's the same apart from the mass of Saturn. Well, if it helps you to understand it that way, fine, but it seems a bit unnecessary. But to Laplace, he never had any such problems, because for him, probability theory is really nothing but common sense reduced to calculation. And so that's the feeling I want you to go away with. Yeah. Sorry, I didn't quite understand.
After Laplace died, did people reject this statement?
They probably forgot about it, yes. Yes. Sorry, some of the physicists have anyway. Sorry?
Did the people stop accepting that the curve is correct? Because it has been drawn from repeated number of experiments.
Yeah.
So the curve is bound to be like that due to uncertainty in the experiment.
Yeah, but it's, I mean, okay, if you start to say, oh, this is to do with, you know, this is maybe some frequency of measurements, well, that doesn't really work either. You know, maybe you only had 4 measurements. So what do you mean by frequency of measurements? And of course, the measurement here is an orbital period. It wasn't a mass anyway. So, you know, it doesn't really help, I don't think. Anyway, so Jeffreys, of course, was one of the few people who carried on and thought Laplace was actually onto the right thing, even though many other people had rejected it. But Cox tried to approach the whole problem slightly differently. And what he was able to do was he was able to show that any method of plausible reasoning which satisfies simple rules of logical consistency has to be equivalent to the normal rules of probability. Now, I'm just going to outline his argument vaguely, not in mathematical terms. So the first thing is you've got a set of propositions or hypotheses, and you want to say how much do you believe one particular hypothesis is true. You don't know if they're true or not. You're just trying to. And so what you want to do is to sort of rank them in some transitive manner. That was his, he took that for granted. He almost didn't state that. Because what you mean by transitive ranking is if you believe A more than B and B more than C, you necessarily believe A more than C. Because if you don't, then you could end up arguing in circles. And a simple way to assign that is to have a transitive ranking is to assign a real number to each proposition to represent how much you believe it. So he starts by saying how to use real numbers. Now, to work out how these real numbers should be manipulated, he put forward 2 assertions which he thought were reasonable. These were his axioms, if you like. Perhaps axiom is too strong a word in a mathematical sense. And his first assertion was that if you tell me how much you believe one thing is true, then you implicitly told me how much you believe it's false. He made no assumption about how these 2 were connected, but he thought it was reasonable the 2 ought to be connected in some way. The second assertion is slightly more complicated. He said, if you tell me how much you believe one thing is true, and then you tell me how much you believe the second one is true, conditional on the first one being true, then somehow you told me how much you believe that both things are true. Again, he made no assumption about how these things were connected, just thought it was reasonable that there ought to be a connection. To work out what the actual connections was, he then used the rules of Boolean logic and ordinary algebra to insist that if you could use the same information different ways, you should come to the same conclusion. This is part of his consistency argument. And what he found was that the only way to ensure consistency was that if the real numbers you had assigned could be mapped into another set of numbers that obeyed the normal rules of probability. So you didn't have to call what your system you're using probability, you can call it whatever you like, but if it had to satisfy these simple rules of logical consistency, it had to be equivalent. Okay, so this is my personal interpretation of probability, if you like. Well, at least the people who taught me this stuff, this is what I gained from them. Because the rules of probability are the same, whether you're a frequentist or a Bayesian or whatever, they're the same rules. The question is really what an interpretation. That affects how you view things and maybe even how you use them. And I'd say the Bayesian interpretation is that a probability encodes a state of knowledge, degree of belief, however you like to call it. And because it encodes a state of knowledge, all probabilities are conditional, because the information available to me may not be the same as the information available to you. So all probabilities are conditional. And I'll show tomorrow one place that previous week I differ slightly, is that I agree that if the information available to us is different, our probabilities will be different. But at least some of physicists think that maybe if we should insist that if two people had the same information, perhaps they should try and assign the same probability. So we sort of use that as a rule to try and guide us to how we might start to assign probabilities. That's a big open question. There's still, but at least that gives us that sort of gives us a starting point of how we might direct ourselves. Okay, so here are the rules. I think you know them all. So this is the probability of X is true given I. I is the symbol I use for all the relevant background information. That information may change with time, but if you want to be explicit, then you can call them I1, I1, I2. You know, you may at different points in time get different bits of information, but I include all that in the relevant background information, I. So probability of X is, by definition, a number between 0 and 1. So if you assigned it to be 0, then you are absolutely sure it's false. If you assigned the number 1, then you're absolutely sure that it's true. And a number between 0 and 1 gives you different degrees of uncertainty. You have the sum rule that the probability of X plus the probability that X is true plus the probability that X is false is equal to 1. And the product rule that the probability that both X and Y are true can be written as the probability that X is true given that Y is true times the probability that Y is true irrespective of whether X was true or not. So those are the basic rules, but using them we can derive lots of other corollaries which are useful for analyzing data, because as a scientist that's my usual interest, is actually analyzing data. One simple corollary which is very useful in data analysis is Bayes' theorem. It comes directly from the product rule, because if I were to switch around Y and X all the way through here, then I would have another statement that the probability that for both X and Y being true, it doesn't really matter whether I say X is true and Y is true, or Y is true and X is true. If they're both true, it's going to be the same quantity, and if you flip around Y and X here, then if you equate this with its counterpart with the Y's of X's switched around, you immediately get to Bayes' theorem. And why this is so useful in data analysis is that it helps us to switch things around with respect to the conditioning symbol. It helps us to relate probability of X is true given Y to probability of Y given X. Because very often as scientists we're interested in knowing what's the probability that a hypothesis is true given these data, but we don't know how to assign that directly. Maybe if we assume that the hypothesis is true, we have some noise model or something, we can get some handle on how much we think the data, how likely the data are given the hypothesis. And it's a Bayes theorem that relates the two. It tells you about other things you have to think about. Probability theory doesn't tell you what to assign. That's the topic of my talk tomorrow. But it tells you how they're linked. And you can't just equate the two. There are other things you have to at least think about. Another corollary that's very useful is marginalization. And that says that if you have two quantities x and y, and you're only interested in one of them, you can work out the probability of x is true irrespective whether y is true or not, simply by marginalizing, simply by adding probability both x and y are true to probability of x is true and y is false. And if you have, here I'm assuming there are only two possibilities, y is true, y is false. You might have a set of alternatives, there might be several of them, and then if there are several alternatives, y1 to ym, which are mutually exclusive and exhaustive, then marginalization generalizes to that form. And if you have a continuous parameter, y can take a whole range of values, then the probability that x takes this value, irrespective of the value y, is just given by this integral. So this is a generalization of the marginalization rule. Why this is so useful in data analysis is when we do experiments, there are always calibration parameters that we need if we're going to compare theory to measurements, but we don't know them that well. So you have to take into account those calibration parameters, but you also want to take into account your uncertainty of those calibration parameters. And it's marginalization rule that lets you deal with it. It lets you integrate out those nuisance parameters, parameters that necessarily have to enter the calculations, but you're not sure about them, but you don't really care about them either. Okay, so what I want to do is, so parameter estimation, this is our generic problem. We have a model, and this model, to describe some data or whatever's going on, this model has m parameters, and I'm going to let those parameters be the m components of this vector x. This is just notation. And we have a set of n data, and I let the n elements of this vector d be the data. So given the data, and given all the relevant background information, I want to know about x. And it's this conditional probability which captures that. So that's what I'd like to get at. But if I can't get at it, then that's where you use the rules of probability to try and relate what you want to other probabilities which you think you might be able to assign. So Bayes' theorem says that if you don't know what to do with this, then you could think about these two, because if you can assign these two, then multiplying them gives you to the posterior probability. You'll notice that I replaced the proportionality, the equality in Bayes' theorem with a proportionality. That's because there's a term in the denominator which I left out, probability of d given I. Since x is what I'm interested in, and the term in the denominator doesn't actually include that explicitly, it's really just a normalization constant, and I can deal with it later if necessary. And so I left it out. And we give these things names, but you shouldn't get too hung up on names, because just remember all things are probability conditional. Just think about what's on the left-hand side, those things you're interested in, and the things on the right-hand side you can assume that are true or given. But people do give them these names. We often call this thing the prior probability. So this represents our state of knowledge about x, given only our background information, but not the data. We do an experiment because it enlightens us, and it enlightens us by modifying our prior state of knowledge or ignorance through this term called the likelihood function, which says how likely is it that you'd observe the data that you did, given these values of x in your prior knowledge, and the product gives you your posterior probability, which is your state of knowledge about x in the light of the data you've analyzed and your background information. So just pictorially, let's think about the prior probability. Well, if we don't know very much, we said the probability is going to be broad. So a simple broadish sort of function is something which is invariant over some suitably large range. So here's, somebody might say, no, x is something between here and here, but I don't know very much else, so we just sort of do something simple. Or someone else might, from other physical or other arguments, say, I know a bit more about x, maybe it should only be between here and here, so you can have a slightly narrower prior. So this is saying your prior state of knowledge was a bit more than before. But you may not like these sharp edges, so you could do something like this. Again, what we're trying to do is encapsulate something we don't know too well, because if you already knew it quite well, you wouldn't bother doing the experiment. So this captures a similar sort of prior information, just doesn't have sharp edges. So this is more uncertain to start with than the sharper one. So you do an experiment and you get the likelihood function. Hopefully the likelihood function will be much sharper than the range over which your prior is essentially flat, because the sharper this is compared to that means your data have told you a lot. And you can see that when this is really pretty sharp compared to that, it doesn't really matter where the edges of this are. When you multiply them together, the product remains unchanged. If your data, if your experiment wasn't that great or didn't relate to what you're interested in so well, the likelihood function will be broader. And if your likelihood function is broader, it may depend now on whether you had a narrower prior or a broader prior. And that makes sense. If your data don't tell you very much, your state of knowledge after the experiment has to depend more on what you thought beforehand. If your data tell you a lot, then it's going to depend less on your prior state of knowledge or ignorance. The illustrations I gave before, the likelihood function was unimodal. It isn't always unimodal, unfortunately. And so here's a simple one I dreamt up. And here, if your prior state of knowledge allows you to limit your x space to this, it'll be great, because there's only one peak in there. Whereas your prior state of knowledge is not so informed, then you've got the problem that you can have to say the answer is either this, around this region, or something like this, or maybe that or that, and it becomes harder to deal with. And you get similar sort of, if you didn't have sharp edges, then okay, this narrow Gaussian doesn't get rid of these completely, but it does squash them down quite a lot, so it has a similar sort of effect. Okay, what I want to do is to show you that you might already have been doing Bayesian calculations, even though you didn't realize it. So what I just said a moment ago is that if you do a good experiment, then you learn a lot, and you hope the likelihood function will be much sharper than the prior. And so an extreme case, an ideal case, if you like, something that's very, very broad, is something that's invariant. Of course, technically, you need to put bounds on it to make it normalized, but for many problems, that doesn't matter. We can start with bounds, finite bounds, and do the calculation and see whether there's a well-defined limit as you let them go to whatever. But anyway, it's broad over whatever's important, and if your prior is uniform, then we can go back to Bayes' theorem and say if that is invariant, then we can absorb that into the proportionality constant. And with this assumption, or this assignment, the posterior probability that we're interested in becomes directly proportional to the likelihood function. So the value of x, which makes your data most likely, also becomes the values of x that are most likely given the data. That's, of course, the classical method of maximum likelihood. So maximum likelihood is a perfectly good Bayesian procedure. The difference is that to a Bayesian, it's not fundamental. It's simply what probability theory tells us to use if we're prepared to make certain simplifying approximations. If we're not, it will tell us to do something else. We can go further if, in addition to prior, which is essentially invariant over the appropriate range, we start making assumptions about the noise characteristics of the data as well. And so one thing people often assume is your noise is subject to Gaussian noise, which is additive and independent. I'll show you tomorrow. You don't necessarily have to make these assumptions, but classically that's what you do. And if you make those sorts of assumptions, then your likelihood function simplifies to something of this form, e to the minus chi squared over 2, where dk is your kth measurement with an error bar sigma k, fk is the value of the data predicted on the basis of your model and x. And so chi-squared is the sum of these normalized residual squareds, and so your likelihood takes that form. If you combine these, so if you assign this for the likelihood, and you have to take that for your prior probability, then your posterior probability becomes directly proportional to this, and you get your largest value of the posterior probability when chi-squared takes its smallest value because of that minus sign. And this is, of course, just the method of least squares, which is probably the most commonly used analysis procedure in the physical sciences. And it's a perfectly good Bayesian procedure, but again, it's the only difference for us is that to us, there's nothing fundamental about least squares. It's simply what probability theory tells you to do if you make these simplifying approximations. And if you don't like the results, then maybe those approximations weren't valid, or maybe there's something else that you need to put in. But it's only the results of those approximations. Before I show you some examples from reflectivity measurements, I talked about these systematic uncertainties or nuisance parameters. So within the least squares problem, supposing x were the model parameters we're interested in, but there's also a calibration parameter in the problem called phi. And so what we want to know is we want the posterior probability of x given d, but not given phi. So how can we deal with that? Well, probability says you could write this as this marginal probability. Given both x and phi, integrate out phi. You can use the product rule to expand this out as probability of phi given, you can, I lost myself here. But believe me, you can write it down like that if you think about it hard enough.
Well, I think you want a conditioning probability x given phi multiplied by the probability phi given d and I.
Yeah, but why have I done it that way around?
This is correct, what you have written.
Yeah.
The next one
Yeah.
doesn't quite follow.
No, I made some strong assumptions in that one. I made some, and that came from how I decomposed it.
And then pushed into the proportional.
Yeah, yeah. I've also implicitly used Bayes' theorem and so on in there. Anyway, that's what it tells you to do. So pictorially, what it says is that if you have x here, I just drawn it as a one-dimensional axis here. It may be multi-dimensional. You get phi here. If you can write down the joint probability, you might get some sort of probability bump. I've drawn it as a Gaussian, but it doesn't have to be. And what probability theory says is that if you want to give your estimate of x irrespective of phi, irrespective of this calibration parameter, what you have to do is integrate this probability bubble along the phi direction, and it's that marginal which gives you your uncertainty in x irrespective of phi.
What would be a physical example of phi?
Phi, okay, if you're supposing you had, you're doing Bragg diffraction, right? And you're measuring angles, and you obviously assume that there'll be, how well is your 0 point calibrated in this angle? Could all the angles be offset by a certain amount? Or if you have a length in a diffraction experiment, how well do you know the length if you're doing a time of flight experiment? Yeah, so you need to marginalize out, and in this example, the marginal uncertainty in phi sig is so much. One thing I want to warn you against, you wouldn't really do this, but when you're learning to start with, you can easily make this mistake, is you might say, all right, let me first of all optimize both x and phi. And you say, that's my best estimate of x, that's my best estimate of phi. You might be tempted to then fix phi at that best optimal answer and just vary x to see what the uncertainty is. That would be the wrong thing to do. What it would be equivalent to doing is taking a cross-section through this probability bubble. And if you took a cross-section in the probability bubble, then you would estimate this to be the uncertainty in x when it should be that. And the reason you get such a large difference here is this is a highly correlated example. In an uncorrelated example, it wouldn't matter. But you may have correlations, and to make sure that you don't overinterpret it, always make sure you integrate it out. Under a lot of analytical approximations, that is done for us. Oops. Okay, so let me see if I get time to give you a few illustrations.
10 minutes.
Okay. So, some of my friends are interested in polymers or gold layers in silicon or whatever. I'm not sure. So here's the setup. So we've got X and Y in the plane of these layers, and we've got Z going vertically. And one way to study what the layers are and what the material is to shine X-rays or neutrons or something at the surface at grazing angles, and as a function of lambda and theta, you measure what proportion are reflected back at you. So your data are reflectivity, and you're then trying to study the scattering length density, or if you like, the refractive index profile as you go down into the sample. And when you do the experiment, the lambda and theta parameters are actually combined into a single factor Q, 4 pi sine theta over lambda. If you remember your diffraction experiments, you know, Young's double slit, that you get a factor similar to that. You might only get a 2 in there. And here's a set of measurements. It's from a substrate, not a very interesting experiment because I'm just trying to illustrate the basic idea. You've just got a simple substrate, so you're not quite sure what the material is, and you're not quite sure what the interfacial roughness is at this surface. And if you calculate the joint probability for the scattering length density, or if you like, the refractive index of the substrate and the roughness, which I would assume to be a sort of Gaussian roughness, you get this probability bubble. And if I'm only interested in the roughness at the interface and not the material, because I know what the material is, if you like, or I don't really care of the material, it's just the roughness I want, then of course you integrate this bubble in this direction, and the marginal probability for the roughness looks like that. So this tells you what you can tell about the interfacial roughness irrespective of what material you're dealing with. Supposing I wasn't interested in the interfacial roughness, I just wanted to know what the material was, so I'm not interested in the roughness, then I integrate this along this direction, and this marginal probability tells me what the refractive index is irrespective of the diffusiveness at the interface. When we do multivariate problems, we sometimes use analytical methods because when doing marginalizations, the problems become numerically difficult. And nowadays, with computing power, people often do that with Monte Carlo algorithms, but an alternative is to use numerical approximations. You often go and find the maximum, look at the curvature of your probability here, and essentially, if you like, try to fit a Gaussian there. As you can see in this example, that's a bad approximation to a Gaussian. And if you were to do that, these are the marginals you would get. And, well, they capture some sense of what the probability is doing, but there are also discrepancies, and that's because that numerical approximation, that analytical approximation wasn't very good in that example. But there are other problems. In reflectivity data, if you go to a sufficiently small angle, you get complete reflection. So I went to small long Q, it would cut off, and reflectivity won't be bigger than 1. And often you don't know what there's an uncertainty about the scaling of this whole thing up and down. And if you've got the critical edge, where you've gone to reflectivity 1, that gives you scale. You know that has to equal 1. And in this problem, of course, I haven't got to the critical edge, so there was an uncertainty in this vertical scaling. And if you allow for that vertical scaling, so you've got a third dimension, you've got the scattering length density of the material, you've got the roughness at the interface, and there's a third dimension in this cube, which is your scaling multiplier. Then if I want to integrate out, the scaling factor is an example of a nuisance factor, and I integrate out that third dimension, then you see this is the marginal probability for those two parameters. If you compare it to before, there isn't that much change in my estimate of the roughness. Here it goes between 0 and 4, goes between a little bit, maybe a factor of 2, but there's a big difference on this scale. This is going from 6.3, 6.35, and suddenly an uncertainty in that scaling parameter leads to a huge additional uncertainty. If I'd got a set of data where you could see the critical edge, then there wouldn't be so much uncertainty, and allowing for that uncertainty wouldn't change the result so much. But in this particular case, it does. Okay, one thing I want to talk about quickly, but I'll talk about this again in my third lecture, which is the very last one. I talked so far about parameter estimation. You have a particular model defined by certain parameters. There may or may not be some nuisance parameters, but you're trying to estimate these optimal estimate of these parameters, the uncertainty. Supposing there was some uncertainty about the model itself. Supposing one person says, this is, he's putting up graphical data, and one person says, I don't see any signal in there. I think the signal was 0. Another person will say, well, I can see it's not changing much, but I'm not sure if it was 0. Third person might say, I don't know, if I look at it this way, it almost seems to be going up, so maybe it's rising linearly. So you haven't got one model, you've got several models, and there may be some question about those. So how do we compare different models? And so what I had previously called probability of X given D and I, if we want to talk about uncertainty models, then we have to certainly start putting it in explicitly. Before, that H was in there implicitly because I wasn't going to consider alternatives. Now I am going to consider alternatives, so I'm going to be explicit about this. So this is what I had previously meant. And the question now is, supposing you have competing hypotheses, H1 and H2, which one is better? And the quantity we want to get at to address that is this ratio. What's the probability that H1 is true given the data compared to the probability of H2 is true given the data? Because if the ratio is very much greater than 1, perhaps larger than 100, we'll prefer H1. If this ratio is very much less than 1, perhaps less than 0.01, we'll prefer H2. And if the answer is of order unity, the analysis is saying, I'm not sure. I mean, that's a perfectly valid result for the analysis to tell you, going back and doing better experiment. I can't.
Question. So
Yes.
if you have two different models, H1 and H2,
Yeah.
then the X's are also different, right? X1 and X2.
Yes, indeed. I'm coming to that. Yes, so if you have different models, they'll have different model parameters and probably different numbers of model parameters. So that's what we want. How do we get at this ratio? As usual, you don't know how to define these. These are always a probability how to relate to the things that you have. So one thing we just do is we apply Bayes' theorem top and bottom. If you apply Bayes' theorem top and bottom, you get this. And you'll notice I got an equality, not a proportionality. And that's because the denominator, normally the denominator of itself, is the same both top and bottom, so we just relate it to itself. And so as usual, Bayes' theorem says when you prefer H1 or H2 like data, does indeed depend on the data, but it depends to some extent on what you thought about the two theories and what you have. Now, if these were models put, theories put by different theorists, you could use their past track records to make that summary. But either one or other is the same. And hopefully you'll probably have to take this to the community, but there's an option in there. But this is where the data enters. Now, I call this the evidence ratio. All these look like the likelihood functions, they're not quite. What I previously called the likelihood not only involves knowing a particular model, it also involves knowing the relevant parameters of that model. And here I don't have those parameters. So once again, how do we deal with this? Try and use the rules of probability related to other things. I should say this term here, the one we want, which is probability of data given hypothesis and not given the values of X, is not a new term. It's a normalization term in Bayes' theorem that only that one. We picked up the parameter problem and we get away with that, but we want to do any quantity pricing problem. So it's not a new parameter. Being a normalization factor, all it was the integral of the numerator over the allowed space. But that's where you have to think more carefully now, because whereas for the parameter estimation problem, when I had a uniform prior, I could often say, as long as it's sufficiently large, as long as it's not 0 in regions with a likelihood, you'd get to the same conclusions. That's no longer true. Even if you assign a uniform prior, you have to think about the bounds. You have to normalize things properly. You have to know what to integrate what space you have to integrate over there. So you're asking a different question, so probability forces you to think about something else. And so what this is really is a average likelihood, okay, the average likelihood weighted by the prior. So the interesting thing to first order is that if you have a given model and you want your best estimate of the parameters, you'll often find the set of parameters which maximize the likelihood. But if you have got different models, you don't compare the best likelihoods you've got, because if you only compared the best likelihoods under the two models, you would always prefer the more complicated model, because the more complicated model will give you more flexibility, allowing you better agreement. And indeed, probability theory says, no, you shouldn't compare the best fit likelihoods. You have to look at compare the average likelihoods. What's the average value of the likelihood? So if you have a more complicated model, it gives you space to give better agreement, but it's going to give you a penalty in having to average the thing over a larger space, and that has to be compensated for. Okay, well, I'm not going to talk about free-form solutions. You can look at the book. I'm just going to say very quickly, so far what we've talked about is you've done an experiment, you've got a model, you're trying to estimate the parameters, or if you've got a model uncertain, you can compare them. But this assumes you've got no freedom to choose the data, the measurements you make. Supposing you're about to design a piece of experimental equipment. Suppose you're designing which measurements to make. Well, probability theory can address that problem too. It can tell you about how best to design your experiment and so on. So the essence of how you address it is very simple. The idea is, if you're doing an experiment to learn something, design something where the data are most sensitive to your object of interest. Unfortunately, putting that simple principle into practice is often very difficult, because what's best will often depend on the precise question being asked. If you're talking about a spectrum, you know, if you are prepared to accept that there are two peaks, and the question is where are they, how big are they, then what's best might be one thing. Or let me take a simple example. Supposing you've got a signal peak in your spectrum, and you're interested in the position and its amplitude, and you want to know how to design it to affect your resolution function. What's best will depend on whether you really want to know the amplitude or whether you want to know the position, because if you want to know the position as well as possible, the analysis will tell you to have a very sharp resolution function. If you want to know what the amplitude is, it'll say make it as large as possible, so you want the big. And so if you want both, you're going to have to use something else to help you decide the relative importance of those two. So it can be difficult in that way. Okay, so because I run out of time, I hope I've just given you a quick flavour, but nothing more than that, that the Bayesian approach to probability theory gives a logical and unified view of data analysis, because when I was a student, one thing I didn't like about statistics was it was just a hodgepodge of recipes. The recipes themselves sort of made sense, but I didn't quite know I should use one rather than another and so on. Whereas if you take the Bayesian view, well, you say, this is what I want to know, this is what I have, these are the assumptions I'm going to make, etc. You state things clearly, you just use the rules, and if the analysis simplifies to maximum likelihood, fine. If it simplifies to least squares, fine. And if it doesn't, well, that's fine too. But because you have a deeper understanding of why you're using certain procedures, to derive them from what you know in assumptions, they're fair. If you don't like the result or you're not happy with them, you can go back and think about were those assumptions valid or were you not quite sure about them. But more often than that, it's because there's something else you know that you haven't put into the analysis. And so an unsatisfactory result from an analysis can actually guide you to a better model, a better question, and so on. So it's a dynamic process. And I said Laplace's view of probability was that it's nothing but common sense reduced to calculation. He didn't say anything of the sort, of course. Being French, this is what he said. Quite appropriate in Pondicherry. But I'm told by my French colleagues what I put down before was a reasonable translation of that. But Laplace was a Bayesian 200 years ago. My PhD supervisor was a more recent Bayesian, and he put it as follows. It's simply a dialogue with the data, and another way to think about it, and in my last talk again, perhaps I'll try and emphasize both these points again. I've had to skip through a lot. If you really are beginners at this and haven't really worked through even the simplest problems, then I do recommend you look at this book, because that's what sort of people I aimed at. The sort of book I wish I had, I was able to pick up and read when I was a second-year undergraduate. So thank you very much.
Couple of quick questions.
Yes, I like the notion of dialogue with the data. One thing you didn't mention was, you really want to have a practical dialogue with the data. You can't really, you wouldn't want to wait for 100 years to get your answer back. So, can you say a little bit more about the computational techniques that have sort of revolutionized Bayesian analysis over the last 10 or so years, and I guess also the speed up you're getting from just computational power from faster computers, for example?
Yeah, I mean, the big fashionable thing, of course, is Markov chain Monte Carlo. I mean, Monte Carlo methods were developed by Metropolis and others, although the talk I went to said Metropolis' contribution was he had the computer on which they were able to do the calculations. But yes, I mean, they're all Monte Carlo is just essentially trial and error, and the Markov chain bit just means, supposing you had a one-dimensional problem, you don't know what the value of this is, you could randomly try, is it this, is it that, is it that? That's a sort of naive Monte Carlo. Another one is you try this value, you want to randomly try another value, but your second trial is randomly in the sort of neighborhood of the first, so your second one depends, and that's where the Markov chain comes in. And there are there's not one, there are many different Markov chain Monte Carlo algorithms. Simulated annealing is perhaps the oldest and most well-known, but genetic algorithms, new ones are always coming up. And they really have revolutionized, because before that the option was, if you had a problem with more than a few parameters, because if you have only 2-3 parameters, I think the brute force ignorance and visual way is the best way to do it anyway, because you get a real picture. It doesn't matter whether it's whether it's continuous or differentiable or anything, you just do it. But if it's more than that, that becomes rapidly inefficient. So before, you were faced with the way of making analytical approximations, trying to find the maximum of this probability curve, hoping that that was the dominant peak, expanding around it in the Taylor series expansion and using that as a multivariate Gaussian as an analytical way. And then the question was, was that a reasonable approximation for that problem or not? But now with the increased computing power, you can just throw the computer at it, and you can tackle more serious problems. And well, it's always trade-off between speed and robustness. Problem with the Monte Carlo things is, yes, eventually it's guaranteed to get there, but the guarantee may only come in many times the life of the universe. But
Anyone else? So we'll break for tea now, and we are behind schedule, so we'll meet at 4:30.